Hey everybody, we're here to talk about the Pendulum Lab. So let's head further into the classroom, a little bit closer to the whiteboard, and chat. Now, the lab is through the simulation from PhET, and there's basically three main components to it. The first one, you are changing the amplitude and measure the period. The second one, you're changing the mass and measuring the period. And the final third one is that you are measuring, changing the length and measuring the period. Either way, it's kind of nice. You can pull this back and swing this. I highly recommend that you use this period timer. It makes it a lot easier to measure this. It also gives you a really nice visual depiction of what one singular period looks like when you start to time this. You can see that true nature of a period being one full cycle. Now, if you were going to measure this with a stopwatch, you also very easily could. For me personally, I think the easiest way is to put this on the slowest mode, which also slows down the stopwatch. You can pull it up to its maximum amplitude. You can release it. And then what we can do is when it gets all the way to one of the edges, I can hit start. Then I'm going to wait for that to come fully back. So it has not completed a cycle yet. It's still going, still going, still going, still going, and then boom. We have now completed one full cycle from where it starts through its path all the way back. Now, once we collect all that data, obviously the only way to analyze it is to graph the data. So let's dive into the graphs. The first graph we have here is amplitude and period. And we can see if we look at the data here, we can see that this looks very, very flat. However, if you are paying attention, you can absolutely see a trend in that data that's there. What's interesting is if you were to collect this data with a stopwatch, if you actually did this, right, versus using the period timer, so either using the stopwatch or doing it in real life, you would never be able to measure with this level of precision, and you would never notice this. You would see this being the same at the exact for all of these different data values. What we'll say for us is looking at this data, a flat graph indicates that there is no relationship between the two variables. Another way to say that for this specifically is as the amplitude increases, we do not see any change in the period. Now, for us, we'll have to put a little asterisk on that because that is in fact true for small angles. So as long as we stay within a small angle, then it does not change. If you keep going on this, eventually you will find a relationship on that. And for us, we're only really worried about a pendulum at a small angle anyway. We're kind of okay with this not affecting the period. Great. Next up is mass. And the next relationship, looking at mass and period, and wow, you gotta love simulated data. Am I right? Like these are all identical, spot on. And you can see we have that beautiful r squared of 0 telling us that there's no relationship here. We can see that beautiful flat trend line, right? So as we're increasing the mass, we're seeing no change in the period. Now this one is a little bit interesting because if we think about this, if we have that system starting and we have, that 200 grams, and then we go up to that 1 kilogram, that system would have more energy, right? Gravitational potential energy would have more of it, but then somehow that system is making the motion in the exact same amount of time. I'm going to challenge you to use your physics knowledge to figure out why that's true. But this is a rather interesting relationship, and it might be something you might want to figure out, or we might want to talk about in the future. But for sure, if I'm having more energy in the system and it's not causing any change in the period, I wonder if we can try to figure out. And I wonder if that's anything like we've ever seen in the past before. Our final relationship that we're looking at is length and period. And for me, I added a 0, 0 on here. I think it makes sense for this graph because no length on here, it would not be able to oscillate or to cycle back and forth. So I think that makes sense. And when you add that 0, 0, wow, can you see that? Even if you take the 0, 0 out, you can still see that shape that's going on there. The r squared is a little bit different. But for me, I like it there. So you can see side opening parabola. To remind you, linearization, side opening parabola would be to square the vertical values, which would be the period, which I've already done. If we scroll down a little bit, boom, we can see, and because, again, simulated data, we get that beautiful r squared of 1 by squaring the period here. Now, with our data analysis, the next thing that we always do after we have that graph is we want to try to build that mathematical model. We want to try to get to that point where we have the mathematical model that we can then use and we can take with us other places. So let's get the whiteboard going. In general, for our mathematical models, we're always thinking about that basic form. We're thinking about that standard basic y equals mx plus b. And for this graph, the y value would be period squared. Period is a capital T. And then we'd have some number. Units on my slope would be seconds squared per meter. And then this would be multiplied by length. The intercept that I have in my graph is 7e negative 0.5. That's a super tiny value, which means that value is negligible for us. Now, okay, so I got this equation, and I like this a lot, but you remember, slope always has to have meaning for us. If the slope doesn't have the meaning, that's a big problem. So we could try to speak slope here. For every meter, blah, blah, seconds squared. You know what that means? Either square seconds, so we don't really have a good understanding of that. But the slope does, in fact, mean something. So I'm going to give you a little challenge here. This is what I'd like you to do. I would like you to get the value for your slope from your graph, whatever that number ends up being. And what I'd like you to do is 4 pi squared divided by your slope. So 4 times pi squared. So pi squared times 4, that quantity, and divide your slope by that. And I'm going to ask you to pause the video here while you get that value. So pause the video, and I'll see you in a second. Did you pause the video? Come on, pause the video. You just gonna wait for me to do it? Come on, hit pause. Great. When I did this with my graph, I got 9.801. Wow, that's a very interesting number. Units on this. So pi does not have any units, being that mathematical constant. And the slope unit does have units, but what would end up happening, and this is end up being meters per second squared. That's even more interesting because that looks like a number that we know, and then it also has the units that we expect. That is, in fact, little g. I think it should make some sense to you that the pendulum is based on gravity. Gravity is the reason the pendulum becomes a pendulum and tries to swing back and forth. So gravity had to factor in somewhere here. At some point, we had to have gravity factor in. Without gravity, you can watch the pendulum not be a pendulum. If you're curious, in the simulation, while the pendulum's swinging, just turn the gravity off, and you just watch the pendulum just go around in a circle, and then that becomes like a UCM thing. So we then take this, if we think about what this is telling us, if I just do a little bit of algebra with this is telling us that the slope from our graph is actually 4 pi squared divided by little g. So let's take that, and now let's try to build that mathematical model. So we would have period squared. We just figured out that the slope was actually 4 pi squared over little g multiplied by L. Now I'm just going to write this a little bit differently for formatting. And I'm going to actually write this as period squared. And this is 4 pi squared. And I'm going to put L over G like this. And now I would actually be happy here. I'd be happy with this. But in general, for equations, we don't like the leading variable to have any sort of modifiers on them, squares or square roots or anything like that. So what we're going to do is square root both sides of this equation. If we do that, we will get period equals, and again, we'll have to square all the things. So 4 squared is 4 square rooted, and then pi squared, and then this would be the square root of L over G. And then if we're thinking about this, really, this is the period for a pendulum, and there's our mathematical model. Check the pink sheet, and you'll find that there waiting for you. So if you ever need to calculate the period of a pendulum, that's how we would do it. Personally, though, man, oh man, I love this version of this equation. I especially like it for things like algebraic reasoning or quick problem solving. Sometimes with square roots, they mess with our brains a little bit. To think like, oh, it's a double. Well, it's not. It's a double under a square root, so it's really radical too. But But now looking about what this is telling me that for a pendulum, there are two factors that are important. The length of that pendulum is important, and also any gravitational interactions are important. For oscillators, one of the big things we talk about is restoring force. What force is responsible for making the oscillator go back to its central point? It's going to go past that, but what is trying to make it go back to that central point? And for pendulum, it is in fact gravity. Now, as we look at this, big takeaways for us. As we alter the amplitude, as long as we stick to small angles, we're not seeing a change. If I increase the mass, we are not seeing a change in the period. That one's very interesting. I would challenge you again to figure that out using your knowledge of physics, maybe some energy, force, kinematics kind of stuff. If I change the length, we do actually find a difference in the period. And it's not a direct increase. It's not a direct relationship between length and period, but it is in fact a relationship between the two. And of course, gravity matters here. Now, it would be difficult in the classroom to alter little g and try to look at the relationship between little g and the period of a pendulum, but maybe we'll have another virtual lab in the future that will look into that a little bit deeper. For now, hope you enjoyed. See you in the next one.